The solar system is situated in a unique region of our galactic environment called the local cloud, or Oort Cloud. The idea of its existence was first proposed in 1932 by Estonian astronomer Ernst Öpik and later independently formulated by Dutch astrophysicist Jan Oort in the 1950s. He suggested that the cloud could explain the paradox of the longevity of comets, which break up when approaching the Sun. Oort explained this process by stating that comets are preserved in a remote region, and it is from here that they can return to the solar system. This cloud represents a section of interstellar gas and dust in which the solar system moves. Its outer boundary could extend from 50,000 to 100,000 astronomical units, AU, equivalent to about 1 light year. It also marks the limit of the gravitational influence of the solar system, defining the Hill sphere, whose radius is approximately 2 light years. The Oort cloud is divided into 2 regions, a spherical outer cloud and an inner disc-shaped cloud. These clouds are thought to contain objects primarily composed of water, ammonia, and methane ices. The scientific community believes that objects in the Oort cloud originated from material that was scattered far into space by the gravitational influence of giant planets during the early development of the solar system. While there have been no direct observations of the Oort cloud, astronomers suspect that it is the source of long-period comets, as well as Halley-type comets, centaurs, and many objects in the Jupiter family. The outer part of the Oort cloud is influenced by the gravitational forces of passing stars and the Milky Way galaxy itself. These forces can direct comets toward the inner solar system. Short-period comets studied by astronomers may originate both from the scattered disk and the Oort cloud. From 2004 to 2012, only a few objects from the Oort cloud were known, such as Sedna, the first discovered object, about 1,000 kilometers in diameter, and 2000 CR-105, discovered 8 years ago, unique for its extremely elongated orbit, with a semi-major axis of nearly 400 AU. Later, other objects were discovered, including C-2014 UN 271, a long-period large comet with an elliptical orbit. There is also a hypothesis about the existence of a giant planet, Tyche, in the inner part of the Oort cloud, and outside its boundary, a companion star to the Sun, known as Nemesis, is believed to exist. Astronomers John Mattis and Daniel Whitmire from the University of Louisiana in Lafayette have repeatedly claimed to have evidence of the existence of the Tyche planet. They base their conclusions on the unusual behavior of long-period comets, which occasionally appear in the inner solar system. According to their hypothesis, if Tyche exists, traces of it should be found in the archival data collected by the WISE Space Telescope. However, some astronomers have expressed doubts about its existence, pointing to insufficient evidence. A more detailed analysis of the data collected by the WISE telescope, which was planned to be conducted over several years, was needed to confirm the hypothesis. In 2014, NASA reported that, according to preliminary data from the WISE telescope, the existence of a Saturn-sized giant planet at a distance closer than 10,000 AU was excluded. It was also found that a new planet the size of Jupiter could not be closer than 26,000 AU, 0.4 light-years, from the Sun. What then does the mysterious bubble conceal, and how might its origin influence the fate of our solar system? How is the formation of the Oort cloud connected to this bubble, and what secrets could this distant part of our solar system hold? The Oort cloud is part of a larger structure known as the local bubble. It represents an area of rarefied hot gas in an irregular shape, located in the interstellar medium within the Orion arm of our galaxy. This structure stretches over 300 light-years and is primarily composed of neutral hydrogen. The gas density in the local bubble is about 1/10 of the average density of the interstellar medium, which is 0.5 atoms per cubic centimeter, and its temperature reaches around 1 million Kelvin, making it a source of X-ray radiation. The formation of the local bubble is associated with the explosions of several supernovae that occurred approximately 10–12 million years ago. According to 2001 calculations, there may have been from 3 to 6 such explosions, or possibly even more. One of the candidates for the remnants of a supernova is the Geminga pulsar, located in the Gemini constellation. However, later research in 2022 suggests that the number of supernovae was 15, and the age of the bubble is 14.4 million years. The solar system has been inside the local bubble for 5–10 million years. It is currently passing through a denser region known as the local interstellar cloud, LIC, located within it. The local bubble has an elongated shape and rises above the galactic disk. Due to its involvement in the galactic rotation, its shape is gradually becoming hourglass-shaped. It is not a solitary structure. Other smaller bubbles formed by lower-density interstellar gas and connected by tunnels adjoin it. How might the influence of such bubbles and clouds affect the future development of stellar systems and the entire galaxy? And most intriguingly, how did our galaxy form? Will scientists ever solve this mystery, or will it remain a secret? The Milky Way, as we know it today, formed as a result of the collision with Gaia Enceladus. But new research has shown that most of the stars already existed at that time. Like other large spiral galaxies, the Milky Way gradually increased its mass by absorbing and merging with smaller galaxies. Stars mixed together, creating a complex pattern that made it difficult for astronomers to understand what these galaxies looked like before the merger. In 2018, astronomers discovered a way to identify stars that were absorbed during the last major merger. These stars orbit around the center of the Milky Way at an angle to the main disk, and their chemical composition indicates that they once belonged to another galaxy, which became part of ours 10 billion years ago. In a new study, scientists tried to determine the size of the Milky Way during its collision with Gaia Enceladus. If the oldest stars in the Milky Way's disk were formed after the merger, it would mean that the galaxy was relatively small at that time. However, if the oldest stars are older, or have the same age as the stars of the absorbed galaxy, this suggests that the Milky Way was significantly larger during the collision. To refine the age of the stars, scientists studied 95 stars using the Kepler telescope. 6 of these stars belonged to Gaia Enceladus, and the rest were from the Milky Way. By measuring the changes in the brightness of the stars over time, astronomers were able to precisely determine their age with an error margin of up to 11%. The results showed that the stars of Gaia Enceladus are slightly younger than the stars of the Milky Way, but all are roughly the same age, about 10 billion years old. This confirms that most of the stars in the Milky Way's disk already existed when Gaia Enceladus passed through our galaxy. However, according to scientists, the collision could still have led to the formation of new stars in the Milky Way. What will happen when it collides with another galaxy? How will this event change the future of our galaxy and its star systems? What secrets will be revealed after this grand collision? And how might such cosmic cataclysms impact the structure of the entire galaxy?